Yeah, this project was a lot of fun. A lot of my research at school has mainly been math, so it was I guess a refreshing change of pace. Um, so right, so I'm sure a lot of people here know that a lot of the success of modern machine learning is built on large volumes of labeled training data. And so the conventional wisdom here is that the more data, the better, right? This allows us to generalize a better to unseen samples. But obtaining labels for data doesn't come for free. There's still a large bottleneck in sort of our model development pipelines. And today we'll be focusing on the image domain, where we've have increasingly complex labels. So the image here is an example from a recent paper where they obtained pixel level labels for human faces, 34 somewhat obscure classes of the face. I'm not sure what a sclera is, but they label it. And so you can imagine having someone provide labels for thousands and thousands of images of this type is a big bottleneck. Not only is obtaining one image or labeling one image kind of expensive, the amount of label or unlabeled data that we have is extremely large. So, obtaining labels both costly. You have to pay the annotators. It takes a lot of time, and then you have to set up infrastructure to audit your obtained labels and whatnot. So, with that being said, the existing amount of labeled data may not even be enough. So a lot of data distributions, much like cats, are long-tailed. And so a fun fact here is this cat holds the world record for the longest tail at over 16 inches. And hails from my home state of Michigan. But that aside, this essentially means that data sets can have a large number of very common examples. So here on the left, we have some pretty standard images of cats. But as we move into the long tail of the data set, there are a small number of rare edge cases. And these edge cases might be very important for us to sort of classify correctly. You can imagine in autonomous driving applications, you probably don't have that many images of like a trash can rolling in front of your car. But hopefully your autonomous vehicle can swerve to avoid those. Not many examples of that. And by definition, this means that only a small number of long-tail data points are used to train the model, meaning in general, there's sort of poor performance and generalization ability to these long-tail samples. So I guess in a more perfect world, what could we do to tackle these sort of fundamental issues? And specifically in this work, we asked the question, what if we had access to an unlimited source of labeled data? Why would we want this? Well, of course, the more the merrier. Having more data allows us to train models that close this generalization gap between our training data and our test data. And within this infinite pool of data, we'll have labeled examples of these long-tailed parts that I talked about. And so this helps us, quote unquote, tame the long tail. So to make concrete steps towards this, I guess, goal, the first step is to be able to synthesize the data points themselves. So in this work, we'll work with images. And in particular, we'll talk about generative models. We work mainly with generative adversarial networks called GANs. These networks produce new images, and they consist of sort of two parts. There's an image generator, which produces new images, and there's a discriminator that is trained to discern between fake or synthetic generated images from the generator and real unlabeled images. And these things are trained in an adversarial manner. The generator will produce an image, the discriminator will learn what's real and what's fake, and it'll force the generator to produce even more realistic images. And the end result is that a generator is capable of producing pretty high quality images. This entire training process uses unlabeled data, which is sort of the key. In particular, we'll utilize a popular generator architecture called StyleGAN 2. And while the sort of minute details of this architecture aren't super important, we'll give a high level overview. And so StyleGAN 2 essentially grows a random input through a series, or by passing it through a series of what are called style blocks. And there's this latent code associated with each image that modulates each style block, and the output is an image. This latent code contains a lot of rich semantic information about the image. It tells you sort of where the eyes and ears are, hair, if there's a hat, etc. And this latent code lives in what we call a latent space, this curly W here. And it turns out this latent space is an extremely rich space. It captures a lot of rich semantic information about the image, to the point where like you could traverse in this space and change attributes of the output generated image. So the example here is that, starting with some reference image, if you move in particular directions, you can make this person look older or younger. And so, yeah, GANs capture a lot of rich semantic information. We have hopefully access to these representations. The next step here is sort of, can we upgrade GANs to produce associated pixel level labels with each image that it produces? And so to unlock this capability, we'll probably need some training data, some labels to sort of inform our GAN how or what particular labels look like. And the key question here is how much training data do we need? Ideally, we'll only need a small number of images, so we don't need to collect or obtain a lot of labels. So for these sort of foundational reasons, interest in synthetic dataset generation has increased in the last few years, and there's been a lot of different approaches that have been proposed. But our work will focus on one particular approach, which is called DatasetGAN. This paper came out, I believe, 2 years ago, and it was very well received. So they utilize GANs as well as their image generating backbone, and they use a small number of labeled images to train a label gen. So how they do this at a super high level is they start with a latent code. They will generate an image, which is sort of the function of the GAN, and then they take this GAN generated image. They ask a human annotator, can you provide pixel level annotations for this image? And so a human is in the loop. They provide pixel level annotations, and we'll call this Y. With this latent code, they also form pixel level representations of each image. So each pixel in the image has a corresponding feature vector. And then with these sort of, and we'll call these representations S. And so with these S-Y pairs, we're able to train a label generator in a supervised manner. And so DatasetGAN was able to produce very high quality labels. It was sort of one of the first, or a very popular approach in this space. But sort of talking about DatasetGAN, there are a couple of drawbacks, and in particular, we'll focus on two here. So as I said earlier, DatasetGAN relies on manual annotations. So you need this human in the loop to label the images that the GAN produces in order to train your GAN or your label generator. This manual annotation process limits the types of labels that we can synthesize. For example, if we want to generate continuous valued labels, having a human annotate an image, each pixel with a continuous value is essentially impossible. Or you'd have to be a lot smarter than me to do that. And second, it imposes a lot of practical drawbacks. to use this framework in a new domain, in a new sort of, or for new labels, you'll need to obtain fresh new annotations of GAN generated images. And this brings us to our second point. The images that are labeled themselves are generated from a GAN. And so this sort of limits our ability to manually curate our training sets, right? We'll need to keep drawing images from a GAN until we receive an image that, hopefully has properties that we may want. And we'll talk about this later when we discuss the long tail. There was a recent work that came out last year that sort of looked at the impacts of training on GAN generated images versus real images in this synthetic dataset generating space. And they concluded that training on labeled GAN images generally results in lower quality generated labels. This is due to a myriad of factors, but sort of the primary one that they point to is that GAN generated images can have small imperfections that, while don't detract from the overall quality of the image, may lead to some weird annotations. For example, I saw one image of a car where the license plate was like taller than it was wide. So unless something has gone extremely wrong, that probably won't ever happen. So using real images, we can obtain more realistic labels. Essentially what we want here is a way to address these two drawbacks, and this is what our work focused on. So if we can draw our training data from existing annotations, then we can produce more complex labels. For example, continuous valued labels. In, say, autonomous driving, you drive around a city and you take images, and you can also collect continuous valued or sort of corresponding continuous value things such as depth information, for example. Since we already have this, there's no sort of associated startup cost if you want to sort of move to new domains where you already have labeled information. And we want these images that we train on to be real images, not ones produced by a GAN. This unlocks a larger pool of candidates for training images, and it also results in higher quality labels. So in all, we need a way to connect real labeled images to the field of synthetic dataset generation. And this is where the field of GAN inversion comes into place. So GAN inversion aims to find a latent code in the latent space of a GAN that corresponds to a real image. And so we're given a pre-trained generator, and there are sort of two paradigms of GAN inversion. The first is encoder-based approaches. These train encoders to map directly from the image domain to the latent space. And these are trained to sort of generalize well. So you'll train these on thousands of images, and hopefully you can sort of apply this at inference time. The advantage here is that these methods have very fast inference time, but the reconstruction quality generally isn't great. So if you pass the obtained latent code back through the generator itself, you'll obtain a reconstructed image, and that, when compared to the original image, may not be as great. And then there are optimization-based approaches. These will directly optimize a similarity-based loss. And so essentially, you'll minimize the loss between the original image and the generator for some latent code, and just find the code directly. The inference time of these methods are slow. There's no way you can, or you have to optimize each image individually. So of course, this takes a lot longer. But the advantage here is that typically your reconstruction quality will be better. GAN inversion was primarily used in the image editing community. I showed a few slides ago an example where if you want to edit a real image, you can GAN invert it, obtain its latent code, and sort of move in the latent space in the way you want to edit the image. So, but for our purposes, we sort of recognize that GAN inversion can be a way to link these real images and their corresponding labels to synthetic dataset generation. And this brings us to our framework, which is called HandsOff. And the idea is very simple. We'll build on the DatasetGAN by inserting a GAN inverter up front. And so the DatasetGAN framework works very well because it works well in that it's trained on a rather small number of GAN generated images. And so by sort of unifying the DatasetGAN paradigm with GAN inversion, we can train a label generator with a small number of real labeled images. And so the key underlying assumption here is that the reconstructed training images align well with their original labels. If this doesn't hold, then we're essentially inserting weird labeling noise into our framework, and things might that might result in some unexpected outcomes. And so at training time, we'll take our training images, GAN invert them to obtain a latent code, pass them back through the generator, and extract the same sort of pixel level representations as DatasetGAN. And from there, we can train our label generators in a supervised manner. And then at inference time, things are pretty straightforward. You take your latent code, you pass it through the generator, you obtain an image, and then from this latent code, you extract this representation, which you can pass through your trained label generator and obtain the corresponding labels. With this process, we can generate labeled data sets of any type of pixel level label. And a lot of our visual examples will focus on semantic segmentation masks. They're sort of the nicest to look at. But later on, I'll show some examples where we do key points and depth maps as well. So before we do anything else, we should verify that our key assumption holds. How well do the reconstructed images from GAN inversion align with the original labels? And so here in the first row, we have the original image. The second row is the output of our GAN inversion process. And the last row is the second row overlaid with the original label. And so this alignment was surprisingly good. When I just ran it the first time, I was actually quite surprised. The sort of high level details are almost perfect. Some of the small details are slightly off. Like for example, this person right here, the tattoo on their neck is slightly smudged in the reconstruction. But that's not sort of a big deal in the grand scheme of things. So we have sort of qualitative evidence here that our assumption holds. So now we can discuss how we actually perform our GAN inversion. We're going to employ a hybrid approach of the two paradigms that I talked about earlier. So there's a lot of great pre-trained or encoder-based methods out there, and we choose to use one called Restyle. But our framework is sort of amenable to any type of GAN inversion you want. This is just sort of how we approached it. So the encoder here produces an initialization. A lot of these, the encoder usually produces images where the high level idea or the high level reconstruction is good, but some of the small details need a little bit of fixing. So we obtain an initial latent code from the encoder, and we pass that through an optimization-based refinement. So that's essentially a starting point for an optimization-based approach. And so this method sort of cleans up a lot of the smaller details, and it results in better alignment with the original labels. So for example, here we have the original image up top. We have the output of our encoder. You can see in this first column here, there's sort of details like the sunroof missing. The shape of the headlamp isn't exactly like the original image. And after running optimization, a lot of these details get corrected so they align better with the original segmentation maps, which are shown on the fourth row. And so there's a concern about inference time here. As I said earlier, optimization-based approaches are slow. You have to optimize each image individually. And this is true. But HandsOff only uses a small number of labeled examples. It's only used once at the beginning of our pipeline. So we can sort of afford to incur the additional computational time, because a lot of the training time of our framework is dominated by actually training things. Cool. So now we've sort of discussed how we connect real images and their labels to dataset generation. Let's talk about how we train our label generator. And like I talked about earlier, the latent code W contains a lot of rich semantic information, but we can form even richer pixel level representations or sort of richer representations that are pixel wise. And so like DatasetGAN will form these pixel level representations. We call them hypercolumn representations here. And what we do is we will start with our latent code, and this random input for an image will pass, or we'll start generating an image, and we'll take the intermediate outputs of each of the style blocks and we'll upsample them to the full resolution of the output image, and then we'll concatenate. And so now sort of each pixel has an associated rather high dimensional feature vector. So in sort of our work, these come out to be 6,000 dimensional roughly. You can play around with keeping only sort of part of the vector, but essentially now each pixel has a very large feature vector that contains a lot of rich semantic information about that pixel. So because these pixel level representations contain this semantically rich information, we can actually get away with training a very simple label generator. So we use an ensemble of very simple 2-layer MLPs, and to train our label generator, we'll get the latent code from GAN inversion, we'll form this representation, and then we'll train the sort of label generator by enforcing a supervised loss for each pixel. So each pixel has this sort of high dimensional feature vector, and we'll train the MLP to label things pixel by pixel. And so once we've trained our label generator, synthesizing image label pairs is pretty straightforward. So like I said earlier, you form the image just by passing your or getting a new latent code and obtaining an image by using the generator as it was designed. But sort of along the way, you extract these intermediate outputs, concatenate them, form your representation, and then for each pixel, you'll pass it through the label generator, and you'll get pixel level labels as a result. So yeah. And so, well, I would like to claim otherwise, but sort of our labels aren't always perfect. So luckily, sort of how we've designed our label generator gives us a natural way to compute sort of a heuristic to measure the quality of the generated labels. So we'll say that a label has sort of poorer quality if there's a high amount of disagreement between all of the MLPs in our ensemble. So for discrete labels like segmentation maps, we'll use like a Jensen-Shannon divergence across all of the output probability distributions. And for continuous labels like depth maps, we'll use variance. And so this gives us a way to compute pixel level uncertainty maps. So for each pixel, you get a measure of sort of how uncertain your label generator is. And so to get a single value for a particular image label pair, you can just sum across all of your pixels. And so here the example is, a man wearing glasses, and the glasses aren't perfect, and there's some weird stuff going on with the shirt that they're wearing. So these sort of hotspots corresponding to high uncertainty are related to the glasses, the shirt area, and then I guess he has a beard and a mustache. So it's confused if that's hair or skin. Yeah, Jiwei.
How do you kind of ensure that all the different
It more or less just works. I mean, like the MLPs are trained with sort of different splits of data, and So like we make no sort of real effort to ensure that all of them produce distinct outputs because that's not sort of ideal behavior. But I guess the idea is if there's like an easy pixel to classify, like the skin, for example, here, then hopefully your outputs should be the same. But it just so happens to work out that like for high uncertainty parts, things get kind of weird. Right. Cool. So now it's time to look at some hopefully pretty plots. So we experimented with 4 different domains. We have human faces and full body fashionable humans here. And then in the next slide, I'll show some with cars and urban driving. And so as you can see with the human faces, we can actually generate pretty remarkably accurate segmentation maps. And then we also have sort of a simpler example of key points in the 3rd row. And sort of we have the same with full body humans. We have segmentation maps and a more complex set of key points as well. There are 2 examples that I really want to highlight on this slide. The first is this human right here. This person is wearing ripped jeans, and HandsOff produces a label that actually classifies the area in the rips of the jeans accurately as skin. So it gets the very minute details correct, which was super cool to see. The second is the person standing next to the first person. This person is wearing like a jacket or something and a t-shirt that are virtually the same color, right? It's black on black, very stylish, but also might be very difficult for a pixel to distinguish what's what. But in the segmentation map here, you can see that it correctly picks out the area that's shirt and the area that's jacket, which was really awesome. And yeah, so we can sort of move now to cars and urban driving scenes. And so for cars, we have segmentation maps only. I think it does a reasonable job here. I wish I plotted these in different colors, but it is actually able to sort of discern between the back windshield and the front windshield. I just plotted both of them in yellow because I'm me. And then for urban driving scenes, which is a particularly difficult domain, it can produce what I would say pretty accurate sort of segmentation maps. We have the row of cars in this image. We have sort of buildings versus skyline versus trees. And so that was really cool. And then, like I talked about earlier, with the driving scenes for each image, we have an associated depth map. This was collected on the car with sensors. And so we were able to train HandsOff to produce these very sort of continuous valued depth maps, range from like 0 to 300 meters or something like that. So things generally line up well, and this was sort of really heartening to see. So while it's fun to look at visual examples, we should also sort of not forget the goal here, which is we want to generate synthetic data to improve or train models on. And so one way we can quantify the sort of quality of our synthetically generated data sets is to follow this sort of approach. So first, we'll train our label generator, everything, and we'll produce a moderately sized data set of 10,000 images. We'll filter out some of the bad examples with the filtering method I showed earlier. And then we'll train a downstream network on our synthesized data. This downstream network will perform the corresponding task like semantic segmentation or segmentation maps and so on. And then finally, we'll take a set of real labeled images. These are real images. They're labeled by humans, akin to your standard machine learning test set. And we'll evaluate this trained downstream network on this test set of images. And so some of the evaluation we'll talk about in the next couple of slides. Segmentation will measure performance in mean intersection over union. That is, for each part, we'll compute the IOU, which is just the amount of overlap that the predicted label has with the ground truth label divided by the union of the two. So under this measure, the higher, the better. And later on, we'll have key points. We'll measure this by the percentage of correctly identified key points. So this is just the number of key points that fall within a certain radius of the ground truth key point. And then for depth, we'll just compute the mean squared error. We have a couple variants here, and I'll show you these in the upcoming slides. So we compared hands-off against a couple of different baselines. The first is DatasetGAN, and the second is a follow-up work to DatasetGAN called EditGAN. EditGAN was built primarily for image editing, but with a few tweaks, you can have it produce datasets as well. And before diving into some of these, the big picture is that across a bunch of different domains for a variety of number of labeled images, hands-off outperforms all the relevant baselines accordingly. We're able to more than triple the amount of training data we use just by taking new images. We don't need to obtain new labels. We don't need to audit the labels. We don't need to have the GAN generate images. This is just taken care of. And so sort of what might draw your attention here is that there are a bunch of X's on this table. And these are places where some of our baselines like DatasetGAN, you can't run this without obtaining new annotations of the GAN generated images. So these were places where sort of we highlight some of the difficulties that DatasetGAN poses. You can't move to sort of new domains. You can't move you can't move to new domains easily, even if you have labeled data in that new domain. And then, so this is essentially an example of generating discrete labels. On the next slide here, we'll talk about continuous valued labels. So for key points, while they are discrete, we use a key point heat map regression framework. So for each ground truth key point while training, we produce a heat map, and then we have hands-off produce a continuous valued heat map. And then from that heat map, we'll pick out the maximum value locations, and those will become our key points. So while these labels are discrete, the sort of process is continuous first. In this setting, we're able to outperform the transfer learning baseline by considerable margins. Essentially, with the key points, we're able to get within a very tight radius of the ground truth key point. And then for depth, the mean squared error is much lower than sort of comparable baselines. Yeah. Yes. Sorry.
Did you keep some data for GAN generator before giving the label or just images?
When producing new sampled images,
when you want to acquire the new data. For that
yes. So essentially, we're trying to use existing labels. So if you want to move to a new domain where you don't have any labels for anything, you of course will need to hand label images. There are advantages to hand labeling the real data itself, which sort of we can have a longer discussion about. But this is essentially for moving to domains where you have labeled data and you don't want to acquire more. Okay. Cool. And so since hands-off, one of the benefits of hands-off is that because we can use existing labeled data, we can sort of manually pick and choose what we include in our training set. So we'll look at one sort of application of this, which is our attempt to sort of tackle long tail semantic segmentation. So the idea is that we want to explicitly add images containing long tail parts to our training set. So when hands-off produces images with those somewhat rare parts, it's at least able to label those correctly. And so in the face domain, we have less than 5% of the images in celeb A have hats or glasses. And so we'll run, we sort of experimented in this setting for semantic segmentation targeting these two parts. The first experiment is somewhat more scientific. It's called our substitution setting. And we start with a fixed training set size of 50 images. And then within these 50 images, we'll vary the proportion of images that have either a hat or have glasses. And we do that separately. So we run one experiment exclusively with hats, one experiment exclusively with glasses. And this is, we essentially wanted to make sure that any gains in long tail performance weren't just us adding more training data. And this is one way of sort of fixing the training set size and trying to isolate the source of performance gains. The second experiment is probably more indicative of how a practitioner would go about doing this. We'll start with a base set of training images that may not contain the long tail part, and we'll incrementally add images containing long tail parts. And in this setting, we add both, we add images of hats and glasses simultaneously. So start with a set, we'll add 5 images with hats, 5 images with glasses, and so on. So the first set of experiments is the substitution experiments. So like I said, we have 50 images and we vary the proportion for either hats or glasses. And the big picture takeaway is that this actually does help us improve long tail performance. The IOU in glasses goes up by about 0.4, and the IOU in hats, while it's still relatively low, I would say 0.2 is better than 0. So there was some significant improvement there. And so the IOU for hats is in the red, and then the IOU for glasses is in the green right there. And what you might notice is that after about 25 samples, at least for the hats, the performance starts dropping. And this is a sort of overfitting phenomena. And this essentially happens because the label generator now starts thinking that everything is a hat. Hair is a hat, skin is a hat, background is a hat. A lot of sort of, we've added too many images with hats. This is clearly not ideal, and sort of this drop in performance sort of reflects that. But I guess regardless, we get some good performance gains here. And importantly, we can conclude that the improvement does not come at the expense of other classes. So a lot of these lines up here, we plotted the IOU or the mean IOU of the non-long tail parts, as well as the mean IOU of all the parts, including long tail parts. And sort of the main takeaway here is everything is flat. This is great. It shows that by improving sort of performance in glasses, this didn't occur at the cost of other equally, or maybe not equally important parts, but at the expense of other parts. Am I? It still shows up on this screen. Not sure what happened. Well, I think it might have been a computer issue.
What happened?
My computer shut down.
Well,
Everything
happened.
Yeah, I mean, I was 2 slides away, so
So you want to, if you're 2 slides away, maybe we can just talk.
yeah.
Okay. So they can hear you, but
Okay,
it was going through yours.
I
It
see.
wasn't going through your computer. It's going through mine.
Great. That's why we did it this way.
Yeah, that's what I did.
Perfect.
Okay. So I switched it to the sort of room microphone, so anyone online can speak. Austin was only 2 ways. Finishing, so we'll just do the Q&A now.
I will say the addition experiments were also good. Then I thank everyone, and yeah.
So I have a question for myself.
Yes.
Consider you have 2 modality, image and something else.
Okay.
And you have labels for the whole set of images. You have labels for part of the second modality. And the other half of the second modality is synthetic data. You didn't have them before generating them.
Okay.
Could you use your hands-off to somehow learn the labels from first modality, the first half of the second modality, to generate labels for the synthetic part of second modality?
I think so I guess the question is if you have images and something else, images you have fully labeled, something else you have partially labeled, and you have a set of unlabeled images. New labels for that modality.
Yeah, exactly.
With method. I guess so. This method targets image labeling. So unless the second modality is images, the answer is probably not. But sort of the ideas in hands-off are somewhat universal, right? Instead of talking about it in a GAN, you can talk about it in, if you have a generative model for your second modality that has some latent representation, then and you have a way of connecting maybe the unlabeled sort of, or the labeled examples there to this sort of latent representation. You can employ sort of the same approach. In practice, I guess it's difficult for me to say without specifics. I mean, the ideas are universal, but the exact implementation is sort of difficult.
Thank you very much.
anyone online can also ask questions if they want.
And Sam, I have a question. Can you unmute yourself and ask the question? Sam, can you unmute yourself? Okay, I'm going to ask this question. Can you repeat how you weed out bad images from page 21 from your slides?
Yes. It'll be a lot easier because I actually made one backup. Yeah, so the idea is that for each pixel, you essentially pass its latent representation through the ensemble of MLPs, and you obtain, let's say, 10 different outputs, each corresponding to one MLP. And the high level idea is you look at the disagreement amongst sort of the outputs of each of the MLPs. So if your output value is continuous, you look at the variance across your 10 MLPs. And if the variance is high, then there's a high level of disagreement. If the variance is low, there's sort of consensus that the output value is correct to some degree. And the idea here is that you can do this for each pixel. And so for each pixel, you compute this uncertainty quantity. And so for a full labeled image, you'll have, height by width amount, a number of these values. And sort of to determine an overall score, mainly for filtering purposes, you just sum across all the pixels, all the uncertainty sort of values for each of the pixels, and you obtain one score for the image. And when we're generating new data, we'll do this for each sample that we do, and then after we've synthesized 10,000 images, we'll find the top 10% with the highest value of uncertainty, and we'll just toss them. We can get rid of them. I can go into more detail for semantic segmentation, but the overall idea is essentially the same.
Samson, thanks. There is another question. Tuan asks, for faces completely reconstructed with the original, what features are left out by GAN plus learn labeler? What features are left out by GAN plus learn labeler?
So this is essentially like when we synthesize human faces, I guess, is the question what features in the image are left out, or is this a question of what sort of labels are sort of incorrect?
Interesting features. Can you hear me? Hello? Hello?
Hello. We can hear you.
You can hear me, right?
Yes.
Okay, I meant interesting features. In other words, if you look at the original, and also if you look at the reconstructed, there seem to be some difference. So I don't know what, but so what do you think?
Okay, so this is a question on GAN inversion. If you invert like a human face and then you reconstruct it, there are small subtle differences, but what are these differences? I think like the small details, I think like sort of the image that I showed had a lot of the high level details, right? You can clearly tell that it's supposed to be the same face, but the small level details might be missing. I think what I've observed just by sort of looking through some of the examples was like the hair might be slightly in a different shape, or like the shape of the eyes might be the reconstructed might be seems a little off. I don't really have anything that is super interesting. I mean, I think like the overall reconstructions were good enough that they align with the segmentation maps or the original labels, and that's ultimately sort of what we had hoped to bear. But I mean, sort of to your question, I haven't really dug super deep into exactly how the misalignment occurs, or sort of, or nor can I really think of a way to quantify this without having to, I guess, investigate a lot of images manually. But this is a good question, and I'm sure one that the GAN inversion community is actively working on.
Thank you.
I have a question, can I ask you maybe partially answered? There are other generative models other than GAN, but like is the GAN inversion thing sort of has some uniqueness that, or can you sort of give another version with a different generative model?
Yeah, this is a good question. So if the online people may have missed it, the question is there sort of potential to move to different types of generative models? I'm sure the one on most people's minds is diffusion models. And yeah, I won't give too much away, but the sort of necessity for GAN inversion here was you need a way to connect real images with sort of very rich latent representations. With GANs, this sort of doesn't come for free. You need to build GAN inverters on top of this. Sort of one of the papers that I referenced looked at sort of the semantic information in sort of the denoising model and diffusion model. And their conclusion was that it also contains sort of the same semantic, rich information. And so the idea there is that sort of the forward and backward process of a diffusion model, you can sort of add noise at will, and then you can sort of do the backwards noise prediction network. And this is actually something that we've started experimenting with already, using these representations and connecting and hopefully getting even better labeled images. Good question.
Okay, if there are no further questions, I'd like to thank Austin once again for coming. So let's just give a nice little cheer for him again. So yeah, thanks for doing this, Austin. I enjoyed the talk, and next week we'll have another CSIP seminar with Ryan Benkert, but for now, we will conclude this one. So yeah.
Yeah, thanks everyone. Sorry that my computer decided to die, I guess. But I promise you that last plot was something special. Yeah, thanks everyone.
All right. Thanks everyone for coming online as well, and goodbye.